Thank you. So, properties of gases. This should all be familiar, right? Why should this be familiar? In chapter, which chapter? It is in chapter 10. It's also chapter 3 when we talk about the matter properties of phases. Right? So all of those were kind of standard. The big one is this new one, this force. All of them exert some kind of force on the container. What is that force? Pressure, right? So that's our particles hitting the sides of the container, and that's generating what's known as our pressure. If we're going to look at gases, one of the things that we'll try and do is step back and look at an ideal gas behavior. Why do we want to look at an ideal gas? They're more predictable if we look at the ideal scenario. And this is a horrible example, but it's a fun one. Okay? You all already deal with ideal systems. Right? There's murderers, right? Axe murderers and all that kind of fun stuff. Okay? And if you focused on all those axe murderers, would you be in this room? Why not? Because you're probably afraid the person sitting next to you is an axe murderer. What do you assume? You assume the ideal system that people aren't these crazy murderings, and we can deal with that normal system. That normal system allows us to manipulate our world a little bit better and exist in it. And when we look at variances, we'll look at those variances when they come up as potential issues. Okay? So we stick with our ideal behavior. What are those ideal behaviors? Number one, this is an interesting one. We assume that our gas particles are incredibly tiny. Okay, how tiny? They are so small, they have no volume. Right, which is kind of an important assumption. If we assumed that we were all gas particles, there's a force being exerted by each of us. Okay, admittedly, I'm having a larger force than you all. Why? Why might I be exerting a larger force on the environment than you? Say it again? I'm moving around. Because I'm moving around, I'm creating more likelihood of impact on the sides of the container. That's why I'm exerting a larger force. So we could look at me having a larger energy as well. That's why I'm hitting the walls more frequently than you are. Right? But let's go back to that volume. We assume no volume. If we're all gas particles, the first person in here did what? Think back. Who was the first person in here? Wasn't me. Okay. You were the first person in. Where'd you sit? Everybody's like, that's a stupid question, Mike. She sat where she's sitting right now. Yeah. Okay, very cool. Next person in. Did you have access to the entire volume of the room? No, why not? She was already sitting there. You mean she occupied space, preventing somebody else from sitting there? Yeah. Which means the more particles that we put into this room, the less space there is to put more particles in. Right? So us as particles take up volume. Which means our system, our calculations become more complicated the more things we put in. Do we want more complicated calculations or less complicated? Less complicated. So what do we assume? No volume. So that means the next person that comes in could very well sit in the exact same seat she's in. Right? That's a weird assumption to make, but it's an assumption that works for most gases. Why would it work for most gases? Say it again. Constant motion. And? We just said about the volumes. They all have the exact same volume. What was that volume? 0. Every particle has 0 volume. The container that holds them has a volume. But each particle has 0 volume. They have a low density. This room is already pretty dense because you can see other people. Right? And if we're constantly moving, that becomes a little bit easier to see how we can occupy every all those individual spaces. But even with us as particles, or larger particles, we would occasionally bump into each other. We can't exist in the exact same space. Right? Gases as a density are so low in density, that mass to volume ratio is so low that the odds of two particles ever trying to exist in the same space is so small that we just call it negligible and we ignore it. Right? That helps to simplify our calculation process. Random motions, all sorts of different directions. They have zero attraction for one another. Right? If particles start to come together, we would start to see a phase change. We'd start to see transition towards liquids, or we'd start to run chemical reactions. That's going to change how we represent things, so we assume no attraction. They collide without losing energy. This is called an elastic collision. Hit and bounce. Right? And then the average kinetic energy of your system is related to the temperature. Right? So the more energy it has, the more motion. Right? That's that direct tie. And then the last thing is this incredibly dumb equality. 1 mole of any gas is equal to 22.4 liters. Right? You are told to memorize this. You officially do have to memorize this. Okay? It will show up in your calculations. Right? Why is it incredibly dumb to memorize this? You are dealing with liters with gases. That's the volume of the container. STP doesn't exist. Well, what is STP? Okay, so cool, we started defining it. Standard temperature, 0 degrees Celsius. Does 0 degrees Celsius exist? Yeah, 0 degrees Celsius does exist. It's 0 Kelvin that we haven't gotten to. Okay, but 0 degrees Celsius does exist. Okay, you can set your freezer to be that temperature. Right? Why is that a problem? You all did a gas experiment last week. Okay, filling up the bag with a bunch of gas. What temperature were you at? 25, 26. The rooms are kind of cold, so they're actually probably closer to 22, but that's fine. Right? Not 0 degrees Celsius. So the temperature at which you run all of your experiments is 20 degrees Celsius. Are we at standard temperature? No, which means the equation is false. Why did we tell you to memorize it? Good question. One I can't answer. Right? What is P? Pressure, standard temperature, and pressure. Right? What is standard pressure? One atmosphere. That's the easiest one to memorize. Don't memorize any of the other units. Right? Because you can just say 1 atmosphere. There we go. It's a lovely unit. That's our standard pressure. When are we at 1 atmosphere? Sea level. Are we at sea level? No, which means the equation is false. Right? Insult to injury, standard temperature, right? Let's just say everybody has a standard temperature, right? If we call it standard, that means what? Say that again? Okay, so we could go with average. We just disproved that. What else could standard mean? Acceptable amount? Yeah, it's the value that everybody accepts. So standard temperature is 0 degrees Celsius. Everybody accepts that. Except engineers. Engineers don't accept it. Except physicists. Physicists don't accept it. Right? Except biologists. Biologists don't accept it. It's not freaking standard. Right? How not standard is it? My wife was working on a reactor. She was trying to figure out pressures and gas flows. We ran through PV equals nRT, which is the end of this whole freaking lecture, right? Trying to figure out why her system was getting weird results. Kept getting bizarre answers out of it. Couldn't figure it out, matched to the experiment. So we were starting to assume there was something wrong with the multi-million-dollar piece of equipment. Come to find out later, when she went back into work, started looking through documentation, it wasn't standard temperature. As soon as you changed the temperature, everything went into alignment. What was the temperature they used? 25 degrees Celsius. That probably makes more sense because it's room temperature-ish. right? But everybody picks a different temperature. So if you're working with gases in the future, make sure you know what temperature and pressure they're referencing, because this system falls apart fast. With all of that, what do you need to do? Memorize. 1 mole is 22.4 liters for a gas at standard temperature and pressure. Right? You are responsible for that. You need to know that. Okay? So, how many liters are needed to hold 2 grams of hydrogen gas? Take a swing. I'll go ahead and pause it. See what you can come up with. I can't remember if we actually did conversions. Did we do conversions last time? Yeah? Okay, so let's walk through how I would go through and do this. What's the first thing you think you should do? Okay. Converting to moles, what's it? So was there something before converting to moles? Yes. What was that something before? We're getting a shout out of a whole bunch of conversions, and I understand where you're coming from with all these conversions, because what are you responsible for doing? Converting. So what's your reflex? I'm going to start converting. Okay. Slow it down. Read the question. What do you want?
We want liters.
I want liters. Did I start converting? No. Liters of what? Hydrogen gas. Right? Hg, hydrogen gas. What's the problem with that? That's also mercury. So we want to use a notation that allows us to not make mistakes and accidentally convert into mercury. So what is our notation for hydrogen gas? H parentheses G. Anybody else want to add to that? Is it H2? I don't know. You tell me. Is it H2 or is it HG? Okay. Is it H2G or is it HG? And if it makes you feel better, it won't. Why? What's that? What's not specified? Actually, it is. Where's that information specified? Hydrogen gas is always H2. How do you know that? You're saying you were born and you knew that? Are there other things that are also H2? Not H2, but by default 2? Oxygen, nitrogen, fluorine, chlorine, bromine, iodine, hydrogen. There's 7 of them. Those 7 elements, you are required to know that unless we specifically say atom, they are 2. They are diatomic. You are required to know that hydrogen gas is H2. Okay? Why is that important? Well, when we work through our calculation, we'll see why that's important when we get to the end. Okay? Or when we get to some part of it. Okay? So liters of H2. Cool. What do you want to start with now? Okay? 2 grams of hydrogen gas. Should I put the 2 grams of hydrogen gas on the bottom? Okay, so you said yes because I'm trying to cancel it out. What did you say?
I said no because, well, I'm not really familiar with this really, but like I feel like you should change it to moles first, right?
Change what to moles?
The grams that you're given to moles and then convert that to liters.
Okay, so what you're suggesting is we break it up into multiple conversions, which is okay. Breaking it up into multiple conversions means you have to memorize an equation and an equation and an equation to solve each of those. If you have the brain power to memorize all of those equations, by all means, absolutely, go ahead and do it. Right? But if you're ever leaving this class and you're like, there's too much to memorize, you put it on yourself, not us. You decided to memorize those equations.
I've actually had us do it that long way.
So dimensional analysis is what we're talking through, but what we want to try to address is why we're placing the things where we place them. If you understand why things appear and where they appear, you don't need a formula. So what is dimensional analysis? Well, dimensional analysis is how you place those things in there. The problem with that is that placement is not inherently obvious until someone asks a stupid question like, where should that be placed? In the numerator or in the denominator? Who asked that question? Okay, I did. Fair enough. Who asked me? A student that was like, I don't understand why you placed it there. I was like, that's a good point. I have no idea why I placed it there either. Well, I did know. I knew because that's how I've done it for the last 20 years. Does that work as a good answer for you? You haven't done it for 20 years. Okay, so let's figure out a placement for this. Is grams the same thing as liters? No. So placing the grams top and bottom is going to be very challenging because I'm trying to make it look like liters of H2. How about H2? So let's look at the substance part of our unit. Is the substance part the same? Is H2 the same as H2? Yeah, where does H2 show up in my answer? In the numerator or the denominator? In the numerator. So where do you think this H2 should show up? In the numerator. So what do? H2. What was tied to that H2? I heard it. Grams. 2.0 grams. Where do we place it? We place it in the numerator so that it matches what I'm trying to aim for. It's a goal. What goes in the denominator? That's an even harder question. Molar mass would be writing out a chemical formula. This is a single piece of given information. When we're looking at each of those sections in a conversion, make sure it is one piece of information. The instant you start combining pieces of information, you've memorized a formula to solve it. So let's look at that. 2.0 grams of hydrogen gas. Is that related to anything else? No, that's it. So what unit shows up in the denominator? No unit, because it's just grams of hydrogen. What number shows up in the denominator? 1, because if I place any other number, is it 2? No. There we go, 1. Is grams of hydrogen gas the same thing as liters of hydrogen gas? So what do we need to do? Convert, yeah. Right? And for people going, well, volume, molarity, you had a bunch of different shout-outs for that. Let's see if the dimensional analysis tells us what we should do. What answer do you want? Liters. Liters of hydrogen gas. Where do the liters of hydrogen gas need to appear? So look at our answer. Where does it appear? Numerator, which means in our conversion, where should it appear? In the numerator. Awesome. Consistency. I want liters of hydrogen gas. Do I know the liters of hydrogen gas? No. Well, dang. So I'm going to have to do a conversion. What do I want to convert to? Ideally, what do I want to convert it to? Perfect world. Perfect world. Do I want grams of hydrogen gas in my answer? No. Perfect world, what do I want it to be? I want that conversion. If I have that conversion, what does that mean? I'm just done. I just run the math. Awesome. Does that conversion exist? Okay, here's where we get an unfortunate no. So now we have to decide, which one do you want to target? Do you want to look at grams or do you want to look at liters? Okay, we heard a suggestion for grams. Loudest down here, it might have been liters in the back. Okay, believe it or not, it doesn't matter. You pick one and you stick with it. Okay? Everybody has a different comfort level when moving through conversions. You will see a different path. You have to find the path that consistently works. So we heard grams. If we are sticking with grams, we're getting rid of the liters and we want to convert those grams into something. What do we want to convert those grams into? Moles. Moles of what? Hydrogen gas. So we ask our question again, does it exist? Yes. Where does it exist? You told me yes, and now you're not telling me where it exists. I don't care about the numbers. Where does it exist? So let's try it this way. You have numbers. Where did you get those numbers from? Where does it exist? It exists on the periodic table. Okay? That's where you're getting that information. Okay? When you're dealing with conversions, dimensional analysis just says how you organize that information. You have to know where that information is found. You have to be able to answer that, does it exist? Those people, a formula is so much easier. Is it? The formula requires you memorize the formula and the conversion factor on where it's found. You're still doing more information with a chemical formula. So when we look at the periodic table, we find our molar mass for hydrogen. What's our molar mass for hydrogen? 1.01. That is for what? How many hydrogens? 1. How many hydrogens do we have? 2, which means 2.02 grams is 1 mole. Yeah? Now what happens? Grams of H2 cancel. This is why a lot of people like doing molar mass, because what just happened? You got rid of something. Yes. Do we have our answer? No. What do we want?
Liters.
I want liters of hydrogen gas. I don't have liters of hydrogen gas, so I'm going to have to convert to something. What do you want to convert to? Why do you want to convert to moles of hydrogen gas? To cancel the previous unit. This is dimensional analysis. Dimensional analysis is selecting those conversions so that this works. We ask the question again, does it exist? Yes, where does it exist? Okay, this becomes a weird one on where it exists. I would argue this exists. I spell that right? In your brain, because you were required to memorize that. If you've identified where these things are found, you now know what to memorize for the exam. If you haven't identified where this information is found, what do you have to do for the exam? Memorize the 4 or 5 chapters of the exam, or of the textbook. Right? That sucks. So start whittling down where that information is found and why you have to have that information. You are required to know that that exists. What is that information? 1 mole equals 22.4 liters. Because I can tell I'm losing you, so let's do some more yelling. Where does the 1 go? No, it does not go on the bottom. Someone's listening. It goes with moles. 1 goes here, and for those people, but that's on the bottom. That's on the bottom now. And if you go through the habit of saying the 1 goes on the bottom, guess what happens when we flip that conversion? You place it on the bottom again, but it's been flipped, and now you're screwed. Associate the numbers with the units. Notice that when we solved this, when did I write the number? After the unit. Every single time. Where's the 22.4 go? Fast learners. 22.4. Now what happens? Grams canceled, moles canceled. What do we have? Liters. What did we want? Liters. When did we want it? 10 minutes ago. Now we can pull out the calculator and now we can do all the math. There's no formulas. There's no I had to divide by molar mass. I have to multiply. It's not there. because dimensional analysis sets it up for you. This becomes the fun challenge with dimensional analysis. Does this work really look all that different from anything you've written down? No. And so what happens is unless you're stepped through this process painstakingly, because admit it, that was a painful 10 minutes, you jump to a formula. Okay?
I got a dumb question just because I did it backwards and I still got the same answer.
So again, to that point, does this work look the same as yours? No. When you say backwards, you just flipped the order behind those.
Just the order that we've been doing, like the
Okay.
what we were saying originally. That's
Does it matter?
okay.
Okay? It ultimately doesn't matter because multiplication is communicative. Right? That old math term, it doesn't matter the order in which we do it. What matters is how we set it up. And if you're setting it up where that order is flipped, that's fine, as long as you know why you placed the things where you placed them. If you don't know why, you're dead in the water. Okay? So you have to understand that why behind that placement. If you've got that, you're good. That can come from memorizing a formula. Absolutely fair game. Okay? How many of you need more chemistry? So there's like 3 or 4 hands. So those 3 or 4 hands will use that formula again. Everybody else, you memorized a formula so that you can forget it in 6 weeks. Seriously, yeah. Does someone say that? That's brutal. Yeah, that's awful. Right? So minimize the amount of stuff that you have to memorize and focus on the how and why things work. You will be better for it. Right? Harder one. How many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid? Whew. That one's a beast. Okay? Took longer than I expected on that last one, so I'll give you 2 minutes. Go. You want to race? No. Okay. I was just checking. So we spent 10 minutes. In those 10 minutes, I did lots of yelling, right? Blah, blah, and all that stupid stuff, right? And one of those things was really make sure that we identify that process. What was our step 1 of that process? Wait. You don't know.
What should it have been?
Yeah. What should it have been? I just walked around. One person had it identified. Okay? You don't have to listen to me. That's okay. Okay? But realize that the words that we're trying to use help to shuttle you in that right direction. And if you choose to not use those directions, that's okay. But you're now running the class on your own. Okay? Just so you're aware. So, all things end with a goal. I want liters of hydrogen. Okay? That's where I want to start. Where's my goal? For those of you being like, dude, I never start that way. Okay? Why are you taking this class? Do all of you have an idea on why you need this class? Yeah? You mean you know a goal before you took the class? Yeah. We always start with the goal. Why are you changing that process as soon as you start running a calculation? You need to know where you're going. Okay? This becomes important because then we can go back and look at what we're given to solve. Admittedly, we got that other question up there that I should have erased, so it made it a little bit clearer. What were we given to start with? Okay, false. We were not given grams. Anybody else want to try again? Grams of aluminum. Why is that important?
It's the amount reacted with the hydrochloric acid.
Okay, it's the amount reacted with the hydrochloric acid. And this one becomes a challenging one as far as placement. Okay, mathematicians seem to argue it's obvious it goes in the numerator, and I still question that logic. Okay, we're starting with that single unit. We're ending with a single unit. So it makes sense to place those things in the same location. Okay? Why is that a challenging one here? More challenging than the last one? What was our measurement unit for the answer? It's a hint. It begins with L. Liters. What was our substance unit? Begins with H. Hydrogen. In our given information, what's our measurement unit? Measurement. Grams. Is that the same thing as liters? No. So I don't have anything that looks the same. How about the substance? Aluminum versus hydrogen. Everything is different. That becomes confusing to deal with. Okay? Is that substance unit critical to your conversion? Yes, and we'll see why in just a second. Are grams of aluminum the same thing as liters of hydrogen? No. So what do we want to do? Convert. What do you want to do in that conversion? Okay? I want to throw grams of aluminum in the denominator. What do I want? Ideal world, perfect space. What do I want in the numerator? Liters of hydrogen. Does that exist? No. Dang it. So what am I going to place up there? Okay? I want to convert to moles of aluminum. Where's that conversion found? Periodic table. 26.98 grams is 1 mole. What unit do I now have? I have moles of aluminum. And I'm working out this calculation to intentionally throw someone under the bus. Do I want moles of aluminum? No. What do I want? Okay, so liters, moles. Is there a conversion between liters and moles? Yes. That conversion comes from our brain. Awesome. For those of you frantically writing, stop. Okay, when is this true? Shush you. When is it true? STP for a gas. Okay? So we go 22.4 liters, 1 mole. Well, look at this. Moles cancel. I'd have liters. What's wrong? Now you can talk. When we look at our units, it's a measurement and a substance. What unit are you trying to cancel out? Moles of aluminum. What unit were you trying to get to? Liters of hydrogen. Yes, I liked the, oh my God, look at that. It's like the substance was important. Yeah. Okay.
Transfer from mole to mole.
Yeah, there we go. We're seeing the pieces, starting to see some clicks come in. We have to understand why we're doing those conversions. The units give you that information. If you've just memorized that process, you will fall very quickly into the trap where you're ignoring the substance.
Why can't you guys just ask the question straightforward?
We did.
Yeah.
Right? The next one behind this, because you're talking, oh, you got to do all this mole stuff, that's crap, why do we have to do that? Literally, what is the point of chemistry? You've been through like 12 weeks. It's science. Chemistry is a science. That's not the point of chemistry. Why do we do chemistry? What's that? Humans? What about humans?
I don't know. Curiosity kills the cat.
Right, but what are we doing? Why are we studying? What are we trying to do? Why are we studying reactions?
Because we can.
Where did this come from? Research? How? I just stared at a rock and boom, iPad.
I mean, there's a little bit of time between those two things, so yeah.
Well, that was, so if I just put a rock on this counter and I wait long enough, it's going to turn into an iPad?
And close your eyes, I don't know.
If that's really going to work, I might start doing that. Literally, the point of chemistry goes all the way back to its origin. Alchemy, right? What was alchemy?
Turning things into other things.
turning things into other things. The whole point of chemistry is to convert one substance to another. How do we do that?
Chemistry and alchemy.
Through a balanced chemical equation. That's how we do it. Why do we use grams and liters and moles? We needed to quantify how we did that. If we didn't quantify it, people were like, you just made that up. Okay? I just put the rock there and said, well, close your eyes. And I threw the rock away and put an iPad down. That's a load of nonsense. That's not chemistry. What we're looking at is how we convert one thing to another. That how we convert one thing to another is a chemical equation. All this other unit junk that's going with it is just how we quantify that process. That's not chemistry. Chemistry is that chemical equation. That's chemistry. The rest of it is just conversions. And even then, what are we doing in that chemical equation? What happens to the aluminum?
Dissolves.
Dissolves? Is that it? It just dissolves?
Dissolves and releases.
I took that block of aluminum and what happens to it?
It's aluminum chloride.
Turns it, you mean I converted it into aluminum? Yes, that's exactly what I did. I converted it into aluminum chloride. It's just a conversion process. That conversion process is challenging because it goes through a substance. That's why the entire field of chemistry exists. How do we convert one substance to another substance? That's it. The rest of it is just the dregs that get dragged along with it. So if we go back to our conversion, I want moles of aluminum to become liters of hydrogen. Does the conversion factor exist for me to convert moles of aluminum to liters of hydrogen? So we go back, brain said, memorize this thing. That's true for a gas. One substance. Is this one substance? No. Which means? Doesn't exist. Okay, so now what do you want to look at? Liters of hydrogen or moles of aluminum? Moles of aluminum, okay. What do I want to convert those moles of aluminum to? Moles of hydrogen. You mean I want to do some chemistry? Hell yeah. I mean, heck yeah. Thank you. You just need to follow me around and remind me. Okay? Yes, this exists. This exists where?
In the equation.
In the balanced chemical equation. So a bunch of people started balancing out the chemical reaction. Okay, it's a chemistry class, so arguably it probably makes a lot of sense, but did we have a reason to do it yet? No. Now we have a reason. So we can go back up to our chemical equation. 6, 3, 2, 2. I've done it a few times, but I get it right?
Yeah.
Okay. So which of those numbers do I want to put in?
2.
I want this too? Why not?
Because that's 2 of aluminum.
And why do I not want aluminum chloride? That's not what I'm looking for. What am I looking for? Aluminum. So that 2 is allowed to get pulled in. That 3 gets pulled in. Make sense? Now what do I want to do? Moles of aluminum cancel. And now what do I want? I don't accept that. I want moles of hydrogen to show up where? On the bottom, so that it can cancel. Can I relate the moles of hydrogen to something else? I want to relate it to liters of hydrogen. Why do I want liters of hydrogen? Because that's the goal. That's the driver. Does this exist? Yes. Where does it exist? In your brain. 4 gases. 22.4 liters is 1 mole. Now what do? Now we can do the number crunch and we have our answer. Make sense? For those people doing formulas, yeah, you can, absolutely. We converted grams into moles, moles into moles, moles into liters. Okay? That's 3 conversions. If you break those down, that's 3 formulas that you had to memorize. It's only 3 things, Mike. Fair enough. Do what you want. Okay? each of those steps increases an odd of making a mistake, particularly entering it into the calculator. How many of you have made a calculator mistake? Okay, 3 people, the rest of you are liars. Okay, we make calculator mistakes up the yin-yang. Minimize your use with the calculator, and you can minimize those mistakes. Make sense? Cool. Units. We just talked through all this. Okay? Where to find your conversion factors is ultimately what it comes down to. Go through every single one of your problems, and where you've got a conversion factor, say, where did I find that information? Identify that location so that when you get to the exam and you see that conversion, you're like, that's what I needed to memorize that. And hopefully you did. Okay? So that you've got the context to answer your question. Okay? There's a bunch of formulas that you could memorize. In theory, they're correct. Atmospheric pressure. Okay, so when we're looking at gases, there's this external pressure pushing on our environment. We're done at 9:45? Yeah, sweet. Okay. So then we just have a bunch of kind of factual stuff. Atmospheric pressure is the gas around us pushing. We can observe this by taking a glass cylinder in a large tub of liquid, fill up that glass cylinder, and invert it in the tub. What happens to the liquid in the cylinder? It falls all the way down? No, some of it still stays in there. Why is it staying in there? Because if I take that same tube with liquid in it, and I turn it upside down and put it over her head, what happens? All the liquid falls out. Well, that's not, well, it might be funny for everybody else. I apologize. Okay. Why is it not falling out when it's in the glass, when it's in that tub? What's that? No.
The weight of the oxygen is pushing down on the outside of it.
Gas all around us is pushing on everything. It's pushing down on the liquid here. Since it's pushing down on that, for this liquid to come out, what has to happen? This liquid level would have to rise. Why can't it rise? Pressure from the top is pushing down on it. Okay? That's our atmospheric pressure. So we could go through and take this apparatus and we could say, well, the pressure here was inches of this liquid, millimeters of mercury, centimeters of mercury, inches of mercury. And we could now quantify gas pressure based off of the height of liquid in that tube. Why do we pick mercury? Well, what happens if I just leave a cup of water out on the counter? It evaporates. The liquid in that tub disappears. Well, if there's no liquid in here, what happens to the liquid in the cylinder? It goes down. So when we're talking about atmospheric pressure, we need a liquid that doesn't evaporate. Okay, there's only a few of them that do it. Mercury does a really good job. That's why we talked about mercury as our substance for this. Okay? This now introduces a way for us to quantify atmospheric pressure, the height of that tube. Okay? Are there other ways that we can quantify pressure? Yeah. There's a whole bunch of them, which is why there's a whole bunch of unit conversions that you could do for quantifying pressure, depending on what system somebody measured. PSI, pounds per square inch. Newtons. Newtons is force. Yeah, so Newtons works. Okay, I need engineers to help me out with the other ones. There's a whole slew of conversions. Okay, depending on your class, you may be responsible for those conversions or not. But ultimately, all that they're coming from is a conversion factor. Do you need to memorize that conversion factor? That's a hard question to answer, particularly for me. That's going to be dependent on your instructor on your exam. How could you figure that out? It's not a bad idea. Check the syllabus. Ask! Just ask! Be like, dude, there's a lot of conversion factors on this table. Do you really want me to memorize all of these? Or are you going to give them to me? Okay. What happens if you don't ask? You don't know, which means you might very well memorize all of that and be useless information. So ask. Talk to your instructor. She will provide that guidance to help you move through it. Okay? Vapor pressure, you'll probably see a little bit later, but this is kind of what we talked about with water. Water turns into the gas naturally. It evaporates. Mercury does not. Okay, so vapor pressure is the amount of gas above a liquid, right? It's pressure. Okay, so it's still a pressure thing. Water has a high vapor pressure, meaning it goes to the gas really, really easily. And if it goes to the gas really, really easily, wind just comes across, sweeps the water away, and now more water comes out as a gas. Mercury has a low vapor pressure, which means none of it makes it up into the gas state. If it never makes it to the gas state, it never gets swept away, which means it stays in the container, and we have our atmospheric pressure measurer. Measurers are worded, right? Okay. There's our conversion, units of pressure. Okay. The big one, 1 atmosphere. Guaranteed you should know that. Right. Thankfully, that's an easy one, right? Okay. The rest of them, they're conversion factors you should ask. I would not be surprised if a conversion showed up on an exam, but they would probably provide the equality. You just have to show how to do that conversion. Okay? So, the fun stuff. All of our variables. Tons of scientists' names show up in this. Okay? Again, this is something you should clarify with your instructor. Do you need to memorize that Boyle is named after the volume-pressure relationship? If the answer is yes, then memorize it. If the answer is no, then don't. Okay? But ultimately, these people were associated with these relationships. That if we changed the volume, pressure changed. If we changed the temperature of the gas, volume or pressure changed, depending on our system. The person who observed that relationship got to attach their name to it. But if we go through and look at this, you'll note that there's a lot of different relationships. Volume is showing up in almost all of these. Pressure is showing up in all of them. Moles is showing up in a lot of them. Temperature. All of these different relationships, some extra smart person went through and said, well, that was a neat observation, that was a neat observation, and if we bring them together, we get a new observation. That new observation, I guess I was just going to write it in. That new observation was that pressure times volume, it's not that. The new observation, yeah, it was. Pressure times volume over the moles times our temperature equaled a constant. That was the new observation. How many of you like dimensional analysis? Yay! Okay. One of the biggest issues with dimensional analysis is fractions. Nobody likes fractions. What do you see right there in purple? A fraction. So maybe let's rearrange that so it doesn't look like a fraction and make it easier. What can we turn it into? PV equals nRT. That gives you all of the relationships above. Okay, what do we mean? Boyle's law noted a relationship between volume and pressure. What was that relationship? Well, rearrange our equation. P equals nRT over V. What happens to the pressure when the volume increases? Right? So that could be a challenge. You're looking at an equation, math. I don't understand. There's too many letters. That's okay. We got a balloon. What happens if I increase the volume? I just come through and I try and stretch that balloon bigger. There's less pressure. There's more area in there. There's less particles or less impacts to the sides of the container. There's less pressure. What happens if I do the opposite? Let's shrink the volume of the balloon. Now the pressure goes up. As I try and squeeze that balloon down, the pressure goes up so much that what happens? The balloon pops. There's so much pressure, the balloon can't handle it and it breaks. Is that in PV equals nRT over V? Okay. Pressure equals a number, let's call it 1, over a volume. Okay. If that volume gets really, really, really big, let's say 100, what happens to our pressure? What is 1 over 100? Big or small? Small. So as the volume gets bigger, our pressure gets smaller. What happens if our volume gets really, really, really small? Right? You're like, I don't know how to do decimal. That's cool. You've got this nifty device that you always carry around with you. Those people being like, it's a phone. Yeah. But the calculator, You can't do that math in your head. That's cool. Don't worry. Just do it. 1 divided by 0.001. What happens? You get a really big number. Okay? So as volume decreases, pressure increases. Those relationships are tied up in PV equals nRT. You just have to do some algebra to shift them around to see those relationships. That's the beauty of PV equals nRT. Do you need to memorize Boyle shows the relationship between volume and pressure? No, if you memorized PV equals nRT. Okay? How do you memorize PV equals nRT? Well, there's 2 stories that I can share to help potentially memorize this. Okay? PV equals nRT doesn't really sound like a word. You could just put the letters together and you get PIVNRT. You'll hear people reference PIVNRT all the time. PVNRT, PIVNRT. Okay? My high school chemistry teacher named her cat PIVNRT. Why? I don't know. She just decided to call it PIVNRT. Okay? She also got pulled over by a cop once because she had a vanity plate, license plate, where it was PV space NRT, and she put an equal sign, like taped up the equal sign, and she got a ticket for altering her license plate. Okay? PIVNRT. There it is. Don't forget it. It has all of your relationships in it. That's the whole gas chapter. All of those major relationships boil down to PV equals nRT, which is known as the ideal gas equation. Okay? What is that R? That R is a constant. Okay? That means no matter what happens with your pressure, volume, moles, and temperature, when you put them into a system, they will always equate out to that value. 0.0821 atmospheres, which is a measure of pressure. Liters is a measure of volume. Moles is a measure of just moles. I know, it was a dumb one. K is a measure of temperature. PV equals nRT. That's where those units are coming from. Okay? So if we change to a different pressure system, does R change? If I change to a different pressure system, instead of it being atmospheres, it's millimeters of mercury. Does the value for R change? So let's write that out. How did we calculate R? It's our atmospheres times liters over moles times Kelvin. If I wanted millimeters mercury instead of atmospheres, if you're saying no, you are then telling me what about this conversion? That's a harder question. I left off a 0? No. If you're telling me the R value is exactly the same, you're telling me you know the conversion between millimeters mercury and atmospheres. And you know it is what? For this equation to be true, what must that conversion be?
29.
That's what it actually is. You're saying it's 1. So when you said R does not change, when you change the unit system, you're saying that this equation is true. And in particular, that millimeters of mercury is 1 atmosphere relationship. Is that true? No. And you know that because?
The actual pressure is 29.9.
The actual pressure, and we go back, at 1 atmosphere is 29.9 inches of mercury. The numerical value will change if you do a conversion. Yes, absolutely true. Is it still going to be a constant? Yes, it is constant for those units at that condition. Okay? So you have to make sure you track your units through. That's a potential question that can show up as they give you inches of mercury, but they ask you to do a conversion through PV equals nRT. If PV equals nRT is in atmospheres, you better make sure your pressure is in atmospheres also. Okay? When do you see that conversion? For those 4 hands that raised their hands? 151. They'll talk about it. The big deal to get out of this, R is a constant. We can rearrange PV equals nRT so we can solve for pressure if we know moles, temperature, and volume. We can solve for volume if we know moles, temperature, and pressure. Just rearrangements, yeah? Anybody going to forget that moles is N? Some people are saying yes. Okay, how could we memorize that moles is N? It's really simple. What is moles a measure of? What is a mole? This is one of those conversion factors you should memorize. 6.02 times 10 to the 23rd, what? Atoms, molecules. Ultimately, it's a particle, some kind of particle. And in particular, it's a counting mechanism of that particle. In fact, it would be the number of particles. That's a mole. The number of particles is a mole. Wait, what was our symbol? N. Why is it N? Number of particles. That's where it's coming from. Right? So, you can do conditions, gases at one condition, convert to gases at a second condition. And this is nice because of the ideal gas law. We know they're equal to each other. We know that R. So where we end up seeing expressions, okay, volume of container is doubled. Assume the temperature in moles are not changed. What happens to the pressure? What do you guys think? Double the container of the volume, what happens to your pressure? Increases. Good, safe answer. A couple other people were volunteering it doubles, and then they backtracked a little bit. Right? Increases is a potential safe answer. If we double the volume of the container, here's our balloon, and we make it really, really big, what happened to the pressure? Right? Did the pressure increase? No, if anything, the pressure decreased. This is why when we try and make it big, what happens? It starts to stretch out in between. Okay? Our balloon doesn't want to stretch that big. Okay? Could we quantify this? Yes. Volume of our container. Volume second, it's called final on I. Final is twice the volume initial. Yeah? Pressure final equals, I don't know. Pressure initial is just pressure initial. I don't know what the numerical value is. Temperature initial equals, how do you know it says temperature final? They were not changed. Moles initial, moles final. What do? We're taking these two expressions that we have up here, except instead of having A, we can say initial. And we could say B is final. And now what do? We just stretch that equal sign all the way across. What can you do with N initial and N final? What's that? If they're the same, then I shouldn't be writing this as N initial. I should write it as N final, right? But if it shows up the same on both sides, what could I do? Cancel it out. What can I do to the temperature initial? Same thing. Now what do? What was I solving for? Pressure final. What is pressure final going to be equal to? Pressure initial times volume initial over volume final. Do I know what the volume final was? Except that's volume initial. Now what happens? Those cancel, and I get 1/2 pressure initial. What happened to our pressure? It cut in half. It decreased. See it? Kind of makes sense? Okay. In 1 minute, our ideal gas law, we could go through and set this up. How many moles of neon gas occupy 2.34 liters at STP? I'll real quickly solve this. It says at STP. What am I solving for? Moles of neon. What was I given? 2.43 liters of neon. Is there a conversion factor that relates liters of neon and moles of neon? Yes, what is that conversion factor? 22.4 liters is 1 mole. We crunch it in a calculator, we get a mole. Why are we looking at it? That had nothing to do with PV equals nRT, right? We could go through and plug all those numbers into our expression. This was our volume. Pressure over RT times volume. Guess what happens if you plug in 1 atmosphere? 0.0821 liters atmosphere over mole Kelvin, and a temperature of kelvins, which would be 273 Kelvin. Guess what it becomes? That stupid thing we told you to memorize. They are one and the same. That conversion that you're told to memorize is a direct result of PV equals nRT. Right? If you're a little bothered by that, I am too. We should have just told you to memorize PV equals nRT. But how many of you like doing all that algebra and calculations? That's why we just tell you to memorize. Okay? With that, I know we're done. Just a couple quick facts. Partial pressure. Partial pressure just says the gas, the pressure of each gas when you add them up is your total pressure. That's it. Okay? Really simple. It's just addition. That's all you got to do.
Could you ask Mrs. Hammy to post this lecture?
I will try and get it up. The issue is pulling it off of the iPad, unfortunately.
She gives us straight from the board.
Yeah. Absolute zero is absolute. Absolute zero is just saying Kelvin reached zero. That's ultimately where it came from. Okay, it's coming out of ideal gases. And I think that's all I wanted out of gases. So that was pretty whirlwind. You do have some questions that you need to ask Dr. Hammy. What were those questions?
Which conversion?
Conversion factors, pressure conversion factors. Do you need to have them memorized? Okay. Potentially asking what level of questions you need out of gases as well is going to become important. Okay? You guys have the exam next week? Yeah? Okay. I will try my best to get this lecture somehow posted to the internet whenever it is, tonight. It'll go faster if you check the YouTube, CGC, Chem Mike. And I think I've got a subs playlist, so find that subs playlist, and that's where it is. All my other lectures are also there if you were curious at that. With that, I apologize because I saw you wanted